So good morning, welcome to the 5th lecture on machine translation. And this lecture is devoted to the state of the art of the previous 10 years or a little bit more. This lecture is devoted to phrase-based machine translation. So here is an overview of the talk. We'll first start with just one slide summary of phrase-based MT. And I'll have to remind you of the log linear model, which is the mathematical basis or statistical basis of that system. And then we'll describe the phrase-based machine translation model as such. So we'll describe the features which are used in this log linear model. And we'll talk about how to obtain them and then how to use them to score phrases. And an important part of the lecture will be devoted to the so-called decoding, so translation with the model. Once you have everything ready, once you have the translation tables, the automatically extracted translation dictionaries, how do you translate a given input sentence? And the last bit is devoted to something which is the actual training in the current or in the proper machine learning terms, and that's the weight optimization, the minimum error rate training. So pak běží. Yeah. So. So let's go to the summary of phrase-based MT. You have seen this slide before. It just tells us that you start with a parallel corpus, which is word aligned. So you have correspondences between individual words. These correspondences obviously don't have to be word for word. So there are sometimes multiple words that correspond to one word in the other language. And you extract the translation dictionary, so to say. This differs from the normal translation dictionaries for humans because it contains many multi-word expressions, and also all these words are fully inflected. So you, in the dictionary, you see the exact forms of words as they appear in the text. And this is the linguistic knowledge which is normally expected to be handled by human users of such dictionaries, but phrase-based MT has encoded all this linguistic knowledge simply into these short phrases. And then, equipped with this data set, you can translate new sentences, new input sentences, and there you choose such segmentation of input sentence into these short phrases so that the replacements are well chosen, and you put these replacements together to make the output sentence as fluent as possible. So, for example, the trigrams should be very likely. So the overview is that phrase-based MT reads the whole collection of parallel data. It extracts puzzle pieces, a huge collection of puzzle pieces, and each of these puzzle pieces corresponds to one source phrase and one target phrase, and you use these puzzle pieces to cover the source sentence. You select the subset of them and the ordering of them so that they best, so that the output sentence seems best. The choice, which of these output options is the best one, is driven by the log linear model. So as you know from the second lecture, we are no longer using the simple Bayes law. When we are defining the conditional probability of the target sentence given the source, we use this equation which sums over defined an arbitrary number of feature functions, and each of these feature functions, the individual HMs, considers the current translation candidate from some point of view. And we'll talk about these features in a second. You score each of the candidates with all the features. Each of these features is associated with a weight, and that gives you the weighted sum of that. Because we are running this equation, we are running this probability estimate within the argmax, we are actually interested in the sentence itself and not its probability. We only want to know which sentence will win in this competition. We don't need to normalize, so we don't need to see how many score points have we allocated, given out to all possible output sentences. So we can only check who has obtained the highest score according to the weighted combination of the features. So that is the log linear model. And the phrase-based model is specific in that it builds upon this important phrase-based assumption. The assumption is that sentences can be translated by translating short sequences of words independently of each other. So with phrase-based MT, you break down the input sentence, the source sentence F1 till J, into K phrases. This number of phrases is something that the model decides on the go. So the same sentence can be translated with short phrases or longer phrases, depending on the match of the sentence with the training data. Then each of these phrases is translated independently of the others. That's the key assumption of phrase-based MT. And then you concatenate the translated phrases, and you concatenate them in some order. And there is one more mapping, the possible reordering, which can be also included in the cost, in the score for the hypothesis. So for some languages, it will be more natural to keep the order of the phrases the same way as they were ordered in the input sentence. For some languages, it is important to make some particular movements. It's important to realize that even if the phrases are translated monotonically, the word order can change within individual phrases. So the phrases are multi-word expressions, and multi-word expressions can do any reordering within those phrases as desired. So I've silently introduced one more hidden variable, the segmentation. So the argmax that we are running ideally would be an argmax over summation over all possible segmentations of the given input sentence. So you have the source words, you are considering the target words, and there are many ways in which you can arrive at the same output words, but through different segmentations. And these different segmentations will give you different scores in the model, because now the feature functions in phrase-based MT have three parameters. They have the input sentence, the output sentence, and also the segmentation. So this segmentation is a hidden parameter in the maximization, and the way this is solved in practice is that this sum is actually approximated with just a max, with just the score of the highest scoring segmentation. So to put it really correctly, we are not searching for the best output sentence given the source sentence, but we are searching for the best derivation of that output sentence. So we're searching for the best segmentation of the input and translation of this segmented input. So this is just to make things really correct. Now the features. So what feature functions are used in phrase-based MT? So obviously the most important one is the phrase translation probability that scores phrases independently of each other. So when the feature function is launched over the whole sentence, given a fixed segmentation already, the feature actually just multiplies the probabilities of individual phrases according to the segmentation. So the phrase translation probability feature is decomposed along the segmentation. And this probability of the now target, because of the Bayes law motivation behind, the probability of the source phrase given the target phrase is estimated from the parallel corpus, and we will see that as a reminder in a second. So this phrase translation probability tells us how good the phrases, each of them alone, regardless of the context, seem to be good translations of the source phrases. Then we have already briefly mentioned that we have various counts. So we have word count, which only considers the number of the words in the target sentence, and that is to give the model some control about the total length of the output, whether it is in general tempted to shorten the output or make it longer. We also have the phrase count or phrase penalty, which considers only the segmentation, and within the segmentation it considers only the number of phrases or number of units into which the sentence is broken. And again, this phrase count or phrase penalty controls whether the system will prefer to use longer phrases or shorter phrases. And this is an important parameter which allows the model to react to the match of the training data and the test data. If the training data matches very well the test data, then in the test data we can expect to use very long phrases, and with fewer phrases there is lower risk to make errors in translation. Unfortunately, if we are in a bad setting where we do not have a nice match, then we would need, and the model has the power to do that, we would need to use shorter phrases, because if the test set is different, then we cannot expect to have long sequences in the phrase table, in the dictionary of phrases, and the system through this parameter, through adjustment of this parameter, silently resorts to using shorter phrases. There is a high risk of introducing errors at the phrase boundary, but the robustness or the recall, the coverage of that system improves. Then one feature which we are not going to discuss in any detail is the reordering model. There are various strategies how to estimate whether the particular reordering of phrases, particular modifications of the order of the segments in the segmentation is good or bad for a given language pair. We can skip that for a moment. And there is obviously the feature which we have discussed in the past, and that's the language model probability. And the language model probability considers only the target sentence, not the source. And if it's an n-gram language model, it simply checks the probabilities of each word given n-1 predecessors of the word. Yeah. So what goes along with the phrase-based machine translation approach is this so-called phrase-based MT pipeline. And the pipeline is the sequence of steps that you need to do if you want to build your own phrase-based machine translation system. So something which was called the training of the phrase-based translation system had these steps. First, you had to find parallel texts, then you have to align them at the level of documents and sentences, and then at the level of words. So this is something that we have covered in quite some detail in the previous lecture. And then you extracted the translation units with their scores. So this is what I have briefly hinted at the beginning, and I'll again repeat in a second. So there you end up with the phrase tables or probability tables that give you the basic translation units and their scores. Then the next step that you had to do was this tuning, and that's choosing the best weight combination so that the individual feature functions are working best together. And this tuning or minimum error rate training, that is the actual training in the machine learning sense. The previous steps, the steps 1, 2, 3, 4, that was just the extraction of parameters from some data. So just some aggregate observation of the data. And the actual training of the model is the estimation which of these parameters are more important and which are less important. And then the inference in the machine learning sense, that is the actual translation. And there you take the input sentence, you break it into known units, those that are listed in your translation dictionary, in your phrase table, and you search for the best combination of those. now how to estimate the probabilities of the most important feature of phrase-based machine translation. That's the feature which considers the translation of the individual phrases. And as I hinted in the previous lectures already, we simply use maximum likelihood estimate. We see how often the given source and target phrases co-occur together. That's the count of their co-occurrences, and we divide that. We normalize that by the antecedent by the count of the observations of the antecedent. So by the count of the source phrase, for example, if we are doing this probability, this direction, when we're predicting the target given the source. In practice, both directions are used, and we have discussed that in the previous lecture. You do actually divide this count of the co-occurrences. Once you divide it with the count of the source phrase alone, and in the second calculation, which gives you another feature, you divide it by the count of target phrases alone. So that is very simple. And these counts, where do these counts come from? That's the slide that you have seen at the beginning. You have your parallel corpus. You have your word alignments between the words, and you extract all phrases up to a given maximum length, which was normally set to 10 words, that are consistent with the word alignment. And this huge list of phrase pairs, that is exactly your set of observations. This is where you do the counting. So you count how often the English phrase this time around was paired with nyní, and how often across the many sentences it was paired with touto dobou, and so on. So you have many possible translations. For the same phrase, you will see which of these translations is most likely later on. Now you only collect the counts and do the division to normalize that to make it conditional probabilities. One thing is important to know pretty well. That's the consistency with word alignment. So the consistency makes sure that no word is forgotten. So to illustrate the consistent phrase, like phrase consistent with the word alignment here at the beginning of the sentence, is nyní corresponding to this time around. An example of an inconsistent phrase would be saying that nyní can be translated as this time only. So this smaller rectangle would not be a valid phrase pair, because there is one word which is also kind of involved in the meaning of nyní. So the word alignments, the points here, indicate which words correspond to the meaning of this source word. And we must not forget any of those. So the consistency with the word alignment makes sure that you extract rectangles so that always, whenever you touch a column, all the points, all the dots in that column are included in the rectangle. And whenever you touch a row, all the dots in that rectangle are there. So similarly, even cannot be translated based on this sentence as dokonce only. To translate even correctly based on the evidence from this sentence, you have to use the two words dokonce ještě. So that is the consistency of phrases with the word alignment. So you extract all phrases, short and long, and they are overlapping in many ways. So you extract this time around, and you are also extracting this time around. They're moving. So if your sentence is shorter than the 10-word limit, then you also extract the whole sentence as one translation unit. And the phrase-based system then has the capacity to simply copy the full output as it has seen it in the training data. So that's there is the general like quality in the average case, because the system is very good at copy pasting, and what humans wrote is the best thing that you can do. And there is also a very strong like robustness of this phrase table, because the same phrase is extracted in many small variations with a few words around, and it's also extracted in the small smaller pieces, so you can reconstruct the same output using the smaller pieces or the longer pieces. So the phrase table is like a robust data structure. It contains the observations in many possible ways. So here is a very short snippet from this phrase table that it illustrates how what everything can be translated to the English phrase in Europe. So we're translating from German into English, and based on the parallel corpus, we have seen in Europa translated as in Europe. We have seen also Europas, the adjective, translated as in Europe, and we have seen in EU translated as in Europe. And the scores associated with each of these phrases are the phrase translation probabilities. So that is exactly what we were talking about. The co-occurrence counts divided by either the count of the source phrase or the count of the target phrase. That's the two directions. And there is also lexically weighted scores of the phrases. And the lexically weighted phrases look at the internal dots of the phrases. So when we are scoring the phrase pair this time around and nyní, we can either do the division of the counts of the phrases as a whole, or we can look how often nyní alone with the word alignment or through the word alignment links was linked with this, how often nyní was linked with time, and how often nyní was linked with around. And if each of these components are common, are frequent enough, then the lexically weighted phrase translation probability will be high. So for this phrase, which is like a multi-word expression, it doesn't make so much sense. Let's look at the end of the sentence, rychlej and full stop, faster and full stop. So this is a phrase which is a longer unit. Also, the smaller units would be extracted as one-word phrases, but now we're considering the two-word phrases, and the lexical weighting promotes this phrase because rychlej was very often seen with faster, and full stop was very often seen with the full stop. So this is a kind of a smoothing technique. So the observations of the phrase counts can be pretty low numbers because these can be very long phrases, and long phrases appear infrequently. And if you are doing the maximum likelihood estimate with low numbers, then there is a high risk that some of these numbers will be very imprecise. So we will be dividing like 2 by 1, and you have a probability of 0.5, and that's like highly exaggerated number. So in addition to these phrase probabilities, which can be too rough, too sparse, the lexically weighted ones consider the individual words. And there, the number of observations of word pairs is much higher. So the lexically weighted scores are reliable even for long and infrequent phrases. And then, so this is the 4 numbers, because this lexical weighting is again used in two directions. And then we have the 5th score, which has been removed only in very late versions of the standard decoder for that, the Moses decoder. And the phrase penalty that was always set to e to the power of 1, so 2.71, and that is just the phrase count. So whenever you're using any of these phrases, you are adding these scores to their appropriate to the appropriate elements of the final score vector. And the last element here, that is the counter. That is something which is counting how many phrases have I used across the hypothesis, the candidate translation. Yeah. So we're moving to the translation. How do we translate with the phrase-based system? The translation has 2 phases. In the first phase, you only consider, you like search your phrase table, and you consider which phrases are applicable for this sentence. And then, with this limited, like restricted database, you do the search, you try to combine the puzzle pieces. So in the puzzle piece analogy, the first one is given the whole bag of all possible puzzle pieces, we select the ones which could help to cover the input sentence. And in the decoding, we are playing around with the combinations of the puzzle pieces, and we're selecting the final small set that we will use to cover the sentence, and also to put them in some particular order. Yeah. So the first stage is very simple. We have the input sentence, geht ja nicht nach Hause, and we have this phrase table where we know how in Europa was translated and so on. So we searched through that huge database of all possible phrase translations, and we search for shorter spans and longer spans from the sentence. So we will see in the database that er can be translated as he, or it can also be translated as it, or it can be translated as comma it and comma he, and then get can be translated as is or are or goes or goes, so, and many more options obviously. And then also these two words can be translated at once with get can be translated as it is or he will be or it goes or he goes. So there are many ways in which the phrase can be translated, and there are also many spans that are considered. And what is highlighted here is what we don't know yet. This is the best selection to translate the whole sentence. So the best choice would be he does not go home. So there is even some reordering involved. The system does not know this yet. The system only found all the puzzle pieces that can be used. So now the main search comes, and that's the second stage of the translation. That's the beam search. So we have here the input sentence, and we have all the possible translation of the short and long phrases, and we start with an empty hypothesis. So the empty hypothesis tells us that we have not translated any of the input words. This coverage vector is still set to 0, and we have not produced any output words so far. Yeah. First, we chose how to start, which word to translate, which word should we start the sentence with. And one option is to start by translating the second word, get, and that can be translated as are. Why not? So this is called hypothesis expansion. We have expanded the initial hypothesis with the word that translates the second word in the input, and that is the English word are. We need to go further, but we also translate the second word differently, and we also can translate the first word first. So the initial hypothesis can be expanded in many possible ways. What I've added now to the picture is the translation of the first word er as he, and also the first word now as it. So there are three hypotheses that cover different source words and produce different translation candidates. And we keep on this expansion of hypotheses. So now the most promising one is the he, based on current estimate of the weights. And we go further and we expand this he with the translation of the third word, ja, which can be translated as yes. He, yes. That doesn't seem as a nice sequence, so maybe this path is not worth exploring. Then he goes, and that looks pretty good. And that was the translation of the get. Or we can translate this ja nicht as does not. So that would be he does not. And then again, we can continue by adding further words. For example, the go, filling the gap in the coverage vector, and then finally translating these last two words, nach Hause, into home. So then, after we do all these considerations and all the possible orderings of phrases, we arrive at a hypothesis which covers the whole output and the whole input, and it if we backtrack it, it will tell us which words should we use. So the path through the search graph back to the initial hypothesis is then the final full output text of the target sentence, the best scoring sentence. He does not go home. Yeah. So now it's important to realize that this search space, the search of possible hypotheses, is pretty big. We have many translation options, and we have many translation options for each particle span, but we have also many spans. So the number of hypotheses, the partial hypotheses that we should consider is actually exponential given the sentence length. This suggests that machine translation is NP hard problem, and it is indeed. Already before 2000, there was a proof that machine translation is NP hard, and it's important to know this. How to prove NP hardness? So this is, I'm just now recalling your basic computer science knowledge. If you are proving NP completeness of something, you have to prove that you can validate the solution in polynomial time and the NP hardness itself. You have to use your task as a black box to solve some established NP complete task. The two reductions that Kevin Knight has illustrated in his paper was the reduction of the Hamiltonian circuit or traveling salesman problem to the finding of the best word order given a bigram language model. So we have this black box that can solve machine translation, and this black box follows internally the bigram language model. Obviously, if a sentence is a good sentence, then the bigrams are going to be likely. So that's why this magical MT system, which performs the finding of the best ordering in polynomial time. So that's the assumption that we have this black box that manages it in polynomial time. So we'll use the bigram probabilities. So we are now given a task, an assignment of the Hamiltonian circuit or traveling salesman problem, and we need to convert it to the assignment to this magical black box MT system that considers bigrams. And that's pretty easy to do. So we are given a graph, and we are given edges in that graph. And the question is whether there is the Hamiltonian circuit that goes through all the nodes, and each of the nodes is covered exactly once. So given this assignment, we convert it to the task in machine translation. We will label each of the given nodes with a word that together form a sentence. Whenever there is an edge in the graph, we will license that bigram in the bigram language model. So we create a bigram language model based on the graph description, based on the set of nodes and edges, and then we run the system, the magical machine translation, which will find the path through this, starting at the boundary node and covering all the words and coming back to the boundary node. So that will be the most likely bigram-based ordering of the words. And we get this solution of the translation task, and based on the bigrams that were chosen, we know the path that was followed in the graph. So we convert the solution of the machine translation subproblem into the Hamiltonian circuit solution. So if we claim that the NP system, the magical black box, can do it in polynomial time, then we have solved Hamiltonian circuit in polynomial time. Yeah, so that's the proof of NP hardness of machine translation because we have reduced and well-known NP complete problem into machine translation subtask. Here is another proof, and that is selecting the subset, selecting multi-word expressions to cover the whole sentence. The well-known NP complete task is called minimum set cover. It's related to the back optimization problem. So what you have as the assignment is a set of nodes. These nodes are now written here as words. So we map them to words when doing the reduction. And you also have a set of sets or sets of these nodes. The task is to find the minimum set of these sets so that all your input nodes are covered. So that's the minimum set cover. And the way we map this to a subtask of machine translation is that we use words in some source language to denote the original nodes that we want to cover. And we use the multi-word phrases, so multi-word translation units, to represent the allowed sets of these source words. So here the reduction goes into the Spanish into English translation, and the input nodes were this con, todo, well, I don't speak Spanish, sorry for the pronunciation, and then ela, hacia, la comida, and so on. The sets that were given up front are the sets of Spanish words. So con todo together can be translated as however, and con alone can be translated as with, and todo can be translated as everything. And this hacia la comida together can be translated as cooked, but also this con hacia se can be translated as obtained. So this is an illustration how the input nodes and the sets can be casted as the question which words should be translated jointly in one single multi-word expression. So we do this conversion. We run the magical machine translation system that chooses the best translation, and the best translation system will say to pick the con todo, then comma, and then ela, and then hacia la comida and y. So the translations of these are however, comma, she cooked and left full stop. Yeah. So again, the magical MT system did this in the polynomial time, so it was able to solve the minimum set cover in polynomial time. If P does not equal NP, then we can conclude that machine translation is NP hard. Yeah. So now we need to fight this complexity, and for that let's look at the slides by Barry Haddow, where we will discuss the hypothesis of recombination, the stack-based pruning, and also the future cost estimation. What we need to do now is to fight the large search space, and if you remember, we were gradually expanding hypothesis, and I was saying that sometimes the phrases are short and translate individual words, and sometimes the phrases are large, cover more words at once. It is obvious that the same input string can be now translated with shorter phrases and longer phrases. So the candidate hypothesis, the partial hypothesis in this example could be it is as two separate like expansion steps, or it is covering the two words at once. So this is the different segmentations. When I was talking about the segmentation as the hidden parameter in the maximization, this is exactly where we should be summing the probabilities of these two paths to know the probability of the it is being the translation of the source phrase, whatever that was. But I've told you the summation is not done in practice. What people do in practice is only choose the high scoring one. These two candidate translations or these partial hypotheses are scored against each other, and the one which will win in the end is the one which is higher scoring in the calculation. Well, if we are searching for the higher score, why do we want to expand the whole trees that further go down from these two hypotheses. So there is no point, if one of these hypotheses, for example, this single step one is higher scoring one, there is no point in expanding all the continuation of this and also all the continuation of this. The continuations are identical. So we can reduce the continuation of the search by a factor of two to half by recombining these two hypotheses. So the system, whenever it constructs a new partial hypothesis, it will check whether it already has a hypothesis which covers the same set of input words and produce the same output. And if this is the case, then it's it's very natural to combine these two hypotheses, so we do not create the second variant. We join them together, and then we expand all the future only once. This type of pruning, it is kind of pruning of the search space. It's reduction of the search space, but I should not use the word pruning. This is a safe modification of the search space. We are not losing anything. We are only ignoring something which will be ignored anyway in the end. So there is no difference in the scores of the future. The future of these two candidate hypotheses is totally identical. Unfortunately, this safe recombination is not sufficient to limit the search space. But before we get to that, let's realize one more thing. We can recombine also hypotheses that do not have the exact same output, but that are sufficiently similar, to put it in simple words for now. So, for example, the input sentence was again something in German, and there is these two candidate hypotheses, these two partial translations. The one was that the first word was translated first as there's an error in the picture. So first, the second word was translated as it, and then the surrounding words were translated as does not. So we have one hypothesis which says it does not. And we have another hypothesis which translated the second word differently. It translated the second word as he. So he does not. So we have two now different hypotheses if you consider the full history. One of them says he does not. The other one says it does not. You have to consider what scores will be used to judge which of these hypotheses is better in the future. So I'll come back to this again in a while, but every of these hypotheses, whenever it's expanded, is scored with the phrase probabilities, the scores associated with the phrase, and also with the language model score. So if we assume that we use a trigram language model, then whatever we attach here, we'll only look at the last two words of this, because the trigram will then have to consider the next word after that. So the short summary is that whenever two hypotheses have the same last two words, and we use only a trigram language model, we can combine them, and it is still safe. The beginning, the difference in the beginning will not affect the scores of the future. So when I was talking about the subtrees of expansion, the future paths from this does not after he, and from this does not after it, the scores in these two subtrees will be identical, because none of the scoring functions will look into some deeper history than the last two words. So the recombination can put together two hypotheses whenever they translated the same source words, so the coverage vector is identical, and the history considered by all the other features is identical. The history which is beyond that, which is out of scope of the scoring functions, whether the beginning was he or it, that is no longer important. So that doesn't make any difference in the scores beyond that. So this is the safe pruning, or safe reduction of the search space. And that is explained here. Also, obviously, the reordering model has to be considered. So there is here is the condition on the reordering model. Here is the condition coming from the language model, and the translation model does not impose any restrictions on hypothesis recombination. But this reduction of search space, it's still not sufficient. What we have to do is we have to do some early pruning. We have to drop less likely partial hypotheses before we are finished. So how does that work? The problem is that if we were putting all the partial hypotheses into one stack, then the longer ones would be always scored lower. And that's because longer hypotheses contain more elements. For example, the language model score that always grows, like the number of n-grams considered in the language model score always grows. Each of these elements in the multiplication of the language model score is a probability, a number between 0 and 1. So the total score of the language model always decreases as we extend the hypothesis. So if all the hypotheses were competing in one queue, then essentially the search would be breadth first. It would first explore all the short hypotheses, and only when it has run out of other short hypotheses, it would move to the two-word ones and three-word ones. And this breadth first is something which would kill us. We would spend endless time in the search because we know that the search space is exponentially large. So the way that this is reduced in phrase-based MT is called stack-based beam search. And here you organize partial hypotheses in a sequence of stacks. And these stacks are designed so that it is guaranteed that we will proceed along the sentence linearly and not exponentially. So we will not explore at every bit, at every step, we will not explore too many options. We'll explore only a limited number of options. And still within the stack, the hypotheses that compete to each other compete in kind of a fair comparison. So the best setup was to label the stacks by the number of source words that were already covered. So in the first stack, there is only the empty hypothesis, which is the only one which covers no input word. Then we have the first stack, and the first stack contains hypotheses that have covered exactly one word. And then further stacks are for hypotheses that covered 2 words or 3 words and so on. And when you're doing the incremental step, the expansion of the partial hypothesis, you are taking a hypothesis from the current stack, and you are adding some new words to that. So you're kind of moving, for sure, you're moving to the higher stacks. And depending on how many words you cover with this one translation option, you either put the continuation, the subsequent hypothesis to the immediately following stack, or you put it 2 stacks apart if you have added 2 words and so on. So every stack contains hypotheses that cover the same number of source words, and during expansion, every hypothesis moves to the higher stacks. And the limitation now comes from the stack limit. That's the constant that you give to the system. And the constant says never store more than 20, 200, or 1,000 candidate translations or partial hypotheses within a stack. So at the beginning, we know that the first stack contained only the empty hypothesis. We expanded. Some of these expansions maybe have covered the whole sentence, so they move directly to stack number 10. Some covered only 1 word, so we have all 1-word translations. If there are more translations, more possible expansions of the first hypothesis than the stack limit, then all the lower scoring ones are discarded. Then when we move to the first stack and we start expanding the hypothesis from there, we know that we will do this at most stack limit number of times. And that is the linear bound for the translation. So you have dropped all the hypotheses which are unlikely given the scores so far. So here's the summary in pseudocode. You place empty hypothesis into stack 0, and then you travel across all the stacks in a for loop, so linearly. And for all hypotheses in the stack, you consider all the translation options. And because there is fixed number of translation options, a limit of those as well, then this can be deemed constant. And then if the translation option fits, if it's compatible with the coverage vector, then you create a new hypothesis and you place it to the appropriate further stack, possibly recombining it. And then if the stack has grown too big, then you can directly prune it and you proceed. So after you have covered all the hypotheses or expanded all the hypotheses from the current stack, you move to the next stack. At the end, your final stack contains only hypotheses that cover all the words, and at the top of the stack, based on the score, there is the most likely translation of the sentence. Yeah. So there is various pruning strategies, like maybe you want to keep at most k hypotheses in a stack, or you can want to keep the best score and hypotheses which are not worse than 10 times the best score or 1/10 of the best score. So here is the complexities, and depending on the number of translation options, we have quadratic complexity in terms of translation options and the sentence length. Yeah. So the translation, the reason for quadratic complexity is the reordering, and if we limit the reordering, if we allow to expand hypothesis only close to the currently translated one, then the number of considered translation options is not as many as there is the length of the sentence. But again, a constant number. So then the whole search reduces to the linear complexity. We have the max stack size and the sentence length, and that's it. Yeah. So one thing is still not quite fair in this allocation of partial hypothesis into stacks, and the not fair thing is that you can have two hypotheses that cover the same number of source words, so they compete on the same stack, but one of them does the easy part first, and one of them does the hard part of the sentence first, and that is the unfairness, because in the end, the hypothesis which now has been doing the easy part will still have to translate the hard words. And the hypothesis, which is now doing the hard part of the sentence, will still have the chance to recover the score by doing the easy part after that, because the easy part is still to be there, is still to be covered. So if we would prune based on the score so far, the coast phase so far, we would probably drop the hypothesis which translates the hard part of the sentence first, and that is not fair, because later on it will have a chance to recover its score. So there is one more score component that is considered, and it is very similar to the or it's identical actually to the heuristic in the A-star search algorithm. So the heuristic is a function which estimates how much you will have to pay to get to the end, to the final point in the future anyway. So this is the future cost estimate. And this future cost estimate, when considered for these easy first or hard first hypotheses, will make the comparison fair. So I said that the easy first hypothesis, the hypothesis which translates the easy words first, will still have to translate the hard words. So it will have a higher future cost estimate. And the other one, the hypothesis which first translates the hard words, will have a lower future cost estimate, because it will later be translating only the easy words. Yeah, so here the example is the tourism initiative addresses this for the first time, and the tourism initiative is a pretty rare thing, so it will be hard to translate. The first time is something which is easy to translate. So based on these scores without future estimation cost, then this translation of the first time seems higher scoring. So the system would keep this one on the stack, and it would prune the monotone translation, and that is something which we do not want. So to estimate the future cost, we will consider only the cost of the translation of the words. So phrase translation probabilities. For language model, we will consider only the production of the output phrases within the puzzle pieces and not on their boundaries. And for reordering model, we just ignore that in the future cost estimation. So the future cost is an optimistic estimate of how much we will have to pay in the for each of the individual feature functions as we proceed with the translation. And it's optimistic because we are ignoring the reordering cost, and we are ignoring the n-grams at the boundaries of phrases. And it's good that it's optimistic. Heuristics have to be optimistic for the A-star search to be correct. So how do we estimate the future cost? This is something that can be pre-computed. So we know we have the translation options table. So we have all the puzzle pieces that translate individual parts of the source sentence. And we can only summarize these puzzle pieces, these translation options, to see how expensive are they, what is the cheapest way of translating the individual words, the cheapest way of translating word pairs, the cheapest way of translating triples of words, and so on. So this is a dynamic programming style algorithm. You fill up a diagonal or a triangular table that will tell you for a given span in the sentence what is the cheapest cost that you will have to pay for sure when you are translating this part of the sentence. Yeah, so that's the future cost estimate, and that's again illustrated on that particular example, the tourism initiative addresses for the first time. Function words are cheaper to translate than content words, so the tourism is hard to translate, and common phrases are cheaper for the first time than unusual ones like the tourism initiative addresses. So then, when you are comparing the two hypotheses that we had at the beginning, one of the hypotheses translated the easy words first. So the first time was the candidate translation. So it picked up the easy words at the end of the sentence. And now it is receiving also the future cost score, and the future cost estimation that is this minus 9.3. So that is the cost that will have to pay anyway to translate the first 6 words in the sentence. So if we consider the score of the price paid so far, which is minus 4.11, with the future cost 9.3, we get the total cost 13.41. If we compare that score with the score of the hypothesis that translates the hard word first, so its score on its own is minus 588, but there is a low future cost estimate because the easy words will still be paid for and it will be a lower price. The total score will be 6 plus 5.88. That's 1198. So the total estimate of the full path once we finish is now better for the hypothesis which started with the hard words first. So now this comparison between the two hypotheses is fairer, and the system has not the tendency of translating the easy words first and then just covering the rest, the hard words randomly at the end because it is like stuck in a dead-end road. So the future cost estimate is there to avoid these dead-end roads. It is to ensure that paying first the higher price is okay if you're doing it for like a good investment. You are translating the hard phrases. Later, the path will be smoother and easier for you. And that's what the future cost estimate summarizes. So there are also other decoding algorithms, such as the A-star search that I mentioned, or greedy hill climbing. Maybe we'll get to that in one of the future lectures. You can also use finite state transducers and other possible searches. The A-star search is the basis for the artificial intelligence in the narrow sense, searching through the space of possible solutions, and A-star search guarantees that it will find the best option if you use a heuristic which is admissible, and admissible heuristic is the one which is always overly optimistic, which never overestimates the future cost. Yeah. So we can skip this and let's go back to my slides. So we have already talked about the scores a bit, and we have talked about the recombination of hypotheses. And here I would like to highlight the difference between feature functions. We've already discussed in one of the previous lectures that some of these feature functions are used for the construction of the current candidate, and some of these feature functions are used for scoring of the current candidate. And there is one more important distinction, and the other important distinction is whether the feature functions are local or non-local. So the general idea of phrase-based machine translation is that you translate by pieces. So you have the whole input, and there is some decomposition happening. So these puzzle pieces, in our case, in phrase-based translation, are the phrases that always cover some words, small number of consecutive words in the input. And you use these puzzle pieces to cover the input. Some of the scoring functions then consider the output in a way which is in line with the segmentation. That's the local features. And some of the scoring functions consider also like properties across boundaries of these puzzle pieces. And that is the non-local feature functions. So to illustrate it here, the local feature functions are those in the red rectangles. So the red rectangles are the puzzle pieces. These are the building blocks that segment the input sentence. The input sentence was Peter left for home. And we have searched the parallel corpus, we have done our word alignments and extracted all phrases consistent with alignment and all that. So we know that Peter can be translated as Peter, left for the two words thing can be translated as a single word odešel, and domu can be translated, domu or home tečka can be, home full stop can be translated as domu tečka. So with each of these phrases, or now rather translation options, because these are only phrases located in the sentence, in the input sentence to cover a particular span of the input sentence. There is some scores associated. One of the scores is the phrase translation probability. That's the first one. Then there is the phrase penalty, which increments by 1 with every new puzzle piece. And there is the word penalty, which increments by 1 with every new well, whatever, maybe that is the output. Yeah, so the phrase penalty increases with every output word. So I think there's an error. So the output word, there's 2 output words. So the word penalty should be 2 for this phrase and not for this phrase. So this is the contributions of each of the scores, each of the feature functions, and you don't sum, you sum them along the puzzle pieces. That's what the total says. And then you apply the weight. These weights are the lambdas in the linear model. This is something that we'll discuss in a second. And you get the weighted combination, and then you sum them to get the total score of the hypothesis. So this all the features that can be calculated for the given phrase alone, without any context, are local ones. So the phrase translation probability, phrase penalty, word penalty, these are local features. The non-local feature here is the language model, and the language model considers bigrams. Some of these bigrams are local as well, and these are, by the way, the bigrams that are considered in the future cost estimation. So this DOMU and full stop, that can be estimated upfront as soon as we are like loading this phrase pair from the disk. But some of these bigrams span the boundaries of the puzzle pieces, of the phrases, this Odeshell DOMU. This bigram can be measured or calculated, this probability can be checked only once the hypothesis puts these two phrases together. So that's why it's called non-local. You cannot evaluate it independent of the context. You have to consider the context of the surrounding hypothesis in the past. Here for the language model scores, the same thing applies. You like sum them. The number of elements in the sum will be different from the number of, or can be different from the number of local phrases, number of the rectangles. There is again some total which is still unweighted. And then there is some weight which is used to mix that total language model feature function codes into the total. Yeah. So that's the distinction between local and non-local features. And now you hopefully understand better the recombination strategy, the recombination of partial hypotheses like Petr Odeshell translating Peter left for, and combining it with some other like Petříček, Pete, another translation of Peter, combining with that. How is that affected by the language model scores and the language model n-gram order? So if the language model used higher order n-gram, then it would span even 3 partial or 3 elements in the sum, and we could not recombine hypotheses until the full history of the needed by the language model would be known. Or yeah. Okay, so now we need to explain the last part, and the last part is the weight optimization, and that is the actual training in the machine learning sense. So you have the phrase tables, you have the language model probabilities, and you are searching the space with the beam search, with the stack-based beam search. And you start with some initial weights. And it's important to realize that because of the pruning in the stack-based beam search, the weights influence which hypothesis will survive. So if your weights are set in an unfortunate way, you are searching in the wrong part of the search space. So we need to somehow find the best balance of the weights, but we need to always retranslate, because with every given weight setting, we would be exploring a different part of the search space. So this is that's the idea. That's one part of the idea of the minimum error rate training. The other part is already included in the title. That's the minimum error. So the scores that we have been talking so far are internal model scores. Based on the training data, we know which phrases co-occur with which phrases, we know which n-grams in the target language are more probable, and we can estimate which candidate translation would be the higher scoring one. We can then give this candidate translation to the user, and the user can tell us whether he likes it or not. And this would be the external score. So the internal score is based on the probability tables built into the model and the weights that are now set for the model. And the external score relies on the reference translation, for example. So it is something which assesses the translation quality after the whole process has been finished and with access to some oracle, some golden truth, how this sentence should be translated. What do we do when setting the weights? We use a small held out data set, which is kind of a future test set. It should mimic the properties, it should closely match the properties of the future test set. And we use this held out set to run the system many times, each time with a different setting of the weights. And we try to set the weights so that we get the best outputs based on the external score and not the internal score anymore. So we are trying to set the weights so that the internal score best matches with the external score. Let's illustrate it here in this summary loop. So it is a loop. You start with some input sentence or a set of input sentences. Now here we are starting with the input speak up. That's the command to be translated into Czech, and we translate it with the current weights, and the current weights are 1, 1, 1. So they are initialized randomly or evenly or whatever. The search space includes these hypotheses. The first one was translated kind of word by word, like speak was translated as mluvíme, or we are speaking, and up was translated as upwards, mluvíme nahoru. So word by word, this hypothesis gets a very good score because the word translations are very nice, but we are speaking upwards as a sentence according to the language model of Czech, mluvíme nahoru, that's a very bad thing to do. So the score based on the language model is very low. And also the phrases are kind of not common, so the phrase translation probability is also pretty low. And there are the weights. So the total score for this hypothesis based on the internal score is 2, because it's 2 times 1 plus 0 times 1 and 0 times 1. So that's the internal score. We have another candidate, this nahlas, which is just like speak up in one word. The language model is pretty happy about this because it's shorter. So that's one thing, and the word translation is not very happy about it because it's like word by word the correspondence is bad, and phrase translation is quite okay. It was seen in the training corpus a few times, these multi-word expressions. With these weights, the total score sums to 3. Then we can get the mluv nahlas. And that that has been seen in the training data as a phrase. So the phrase translation probability is very happy about it. For the language model, it is something not really seen often in like news text. So it is okay, but the word translation probability is mediocre because the translations are not very frequent word for word. And here we arrive at the final score of 4. Then we have the 4 hypotheses and so on. So right now, based on the current weights of 1, 1, 1, the highest scoring candidate would be this mluv nahlas. And it turns out that based on the reference translations, people would rather the translation to be more polite, to say, could you please speak up? So the external score says that, well, we are speaking upwards is a very bad thing. This short one, just like speak up, exclamation mark, that's kind of okay, but not the best one. This mluv nahlas for some reason is not scored well. And the polite one, could you please speak up, is the one that externally, based on the external measure, should be chosen. So we now need to somehow modify the model so that it would ideally arrive at the solution that the user wants. And changing all the internal parameters, like the probabilities within the word translation and language model scores, that would be too much work. That would be too many numbers to juggle with. So this is what is not done in phrase-based MT, but it is actually what is done in neural MT. So there you really go into all the internal numbers of the modal components. Here we leave the modal components intact, and what we change are only the weights. So there is the algorithm by Franz Josef Och from 2003, which finds the new weights in such a way so that the external score will now better match, so that the internal score comes out different, and the internal score will better match the external score. So, for example, instead of 1, 1, 1, if we would set the weights to 2, 3, 1, so we increase the importance of the language model, then the very fluent hypothesis with the politeness, polite, please, could you please speak up, will score higher, and then in the weighted sum it would come as the top hypothesis. So by tuning of the weights, we can change the order of the hypothesis, and we can make sure that the hypothesis that the external score likes better will be also scored better by the internal score. So we then retranslate with these phrases, and that is to be sure that in this new setting of weights, we are still in the same part of the search space that we were before, so that we are the pruning that is performed during the beam search will not change its mind, like that we will still find the same hypothesis. So we will translate again with the new weights. So some new hypothesis will probably arise. We will score them, and we will again check whether we need to update the weights or not. So we will find the new weights based on the new set of hypotheses. And then if we do this twice and get the same best weight setting, then we will say, okay, we're finished. We have found the best solution. And that's it. If the weights would differ, we would have to still retranslate. Here is an illustration of the effect of weights on the hypotheses that are considered. So remember, there is about 13 or so weights, or maybe 9 weights in the baseline phrase-based model. The two most important ones, the two most important ones are phrase translation probability and language model score. And what I'm illustrating here is the language model score and the phrase penalty. So the phrase penalty controls whether the system prefers many segments when segmenting the input sentence or a few segments. So if the phrase penalty, or actually the phrase bonus here, if the phrase penalty is high, then for whatever the input sentence was, the candidate translation was this very piecewise one. Na verdict je to ještě závěrečné. So each of these phrases was translated independently of the context. If the phrase penalty or phrase bonus is set to be very low, then it is trying to translate the sentence with as long pieces as possible. Verdict ještě není konečný, a so there is only 1, 2, 3 instead of like 6 or 7 phrases. So that is the phrase penalty. And the language model score must not be exaggerated, because then the system would start fabulating. Then it would prefer nice sentences regardless what the source sentence was saying. So it has to be set reasonably, but it must not be negative. So if you are a Czech speaker and if you start looking at the negative language model score, so at the candidate translations when the weight for the language model score is negative, then you will see that based on the this is fixed input, based on the fixed input words, suddenly our request to produce the strangest possible Czech sentences allows the system to consider candidates which mentions not the court with Yulia Tymoshenko, but rather the beer brewers, twins, and package wrapping companies. All these words, the beer brewers and twins, are licensed according to the phrase table. So there is a lot of garbage in the phrase table as well. But this garbage can suddenly, with bad weight setting, can arise. And it can be selected in the beam search if the weight combination is very strange. So if the weight combination is very strange. So you need to find the good balance of weights so that the quality of the output sentence, the fluency of the output sentence is not too bad, but not exaggerated, so it doesn't fabulate. And also the segmentation of the input sentence is reasonable. And I was already talking about this. So if your test data matches very well your training data, then the phrase bonus can be pretty low. The phrase penalty, in other words, can be pretty high. So it's good to use long phrases if there is the good match. If there is the bad match between the test data and the training data, then it would probably be better to use shorter phrases and translate individual words. So the held out set on which the minimum error rate training is done should really match your test domain. It should be extracted from your test data and not from your training data, so to say. But if you don't know your test data upfront, if you're in a competition or if you're serving translations to the user, you should ask for a development set which is a good illustration of what inputs will be coming in the real run. So there was also one approach of domain adaptation in phrase-based MT that exactly did only weight adaptation for a given new development set. Yeah. So two-strong language model weight leads to words dropped. Negative language model leads to obscure wordings and very strange words appearing there. Higher phrase penalty chop sentences into more segments. So I would just like to highlight that if you ever considered to use phrase-based MT, then the best implementation is this Moses decoder, and there is an installation tutorial. These days, people in machine translation do not longer use phrase-based MT, so everybody uses neural MT, but phrase-based machine translation and Moses decoder are still a very useful tool for various mappings of sequences. So it is now being used in linguistic analysis. For example, if you want to port some tree bank annotation across languages, then you can use the phrase-based translation system because it is more literal translation than what neural MT would do. So it is still a good sequence-to-sequence transfer system, except that the built-in assumption of phrase independence is too strong for natural languages. But this phrase independence assumption is something which can be very, very valid for other tasks. So Moses is now not really used for machine translation, except for languages with extremely small data or for initial phases of unsupervised machine translation. And we will probably get to that in the future lectures. But if you have a large parallel corpus, there is no reason to stick to the assumption of phrase independence. So here's a summary of the lecture of today. We have described the phrase-based model. The phrase-based model is a log-linear model, and the critical thing is this decomposition. That's the key assumption that the whole sentence can be translated by translating the individual pieces of that. And the search, then, we have discussed that in detail. The search has two parts. The first part is just lookup of which of these puzzle pieces are relevant for the input sentence. So, for example, the same phrase can appear several times if there is the same word repeated in the input sentence. So the same phrase becomes multiple translation options. Translation options are phrases identified and located as possible candidates for spans of the input sentence. And then these translation options are considered in the main part, which is the stack-based beam search, where you are putting these pieces together, deciding on their reordering, gradually expanding the hypothesis. And to train a phrase-based MT system, you need to do your preparatory steps. This is the alignment up to the word level, as discussed last week, and then the extraction of your parameters. So you extract and score phrases which are consistent with your word alignment. Then you need to obviously do the same extraction for language model and other possible features. And you run the optimization on the held out set. So that is the actual training. There you set the importance of the individual components, and in translation you just do the beam search as we discussed it. You cover the input with translation options, and you gradually expand hypothesis. The best implementation to use is the Moses decoder. Okay, so that's it for today. I'm looking forward to any of your questions, and also see you next week. Thank you.